It already hurts. It's going to hurt so bad today. If you thought it hurt bad last time, it's going to hurt way worse today. But I always like to give you, before we descend deep into these dark tunnels, a light. It's my turn to talk. You had your turn. It's my turn. But I'm going to give you a light, and that is, if we get there, and I hope we will, at the end of the really terse discussion, we'll get to a point where I'll start doing something and you'll all be like, yes, I know exactly what you're going to do. And you'll all feel really good. But we got to get there first, okay? So let's go through a little bit of pain and suffering together.
Alex, we're not suffering, we're struggling.
Let's get through some pain and struggling together. Thank you for that correction. We're not suffering, we're struggling. What's the difference?
I don't actually remember.
You do not suffer towards a goal. You struggle towards a goal. You struggle to achieve things. Suffering is not achieving anything. So we are struggling together. We are not suffering together. Okay. So a couple of points about what we talked about last time, part of which will carry over into our discussion today. We talked about if we have some space M, then part of the procedure for demonstrating that that space is actually a manifold involved setting up charts, an atlas of charts, the union of which covers the entire space, and then we talked about how in the overlap regions we have to have these transition functions between, say, this chart and this chart. Those are defined in the overlap because this is the part of the space which is common to these two. So those transition functions have to be CP differentiable. So if we might want to have a smooth manifold, we take P to be infinity, so they're infinitely differentiable. But one thing you might notice is, like with the atlas of charts that I've drawn here, you know, we might have one here and then one here, and that covers the whole thing. There's only like certain splotches where you actually have overlap. Like this place down here is not an overlap. So that might lead you to the idea that you only have to have this smoothness criteria for certain regions of the space. That's the regions where you actually have charts which are overlapping. Okay? That's not a very strong sort of smoothness criteria for the space. And this is one of the reasons why our definition in terms of a maximal atlas becomes useful. Because remember, for this to be a manifold, we don't just want a single chart, but we actually, or a single atlas, we actually want a maximal atlas. That is, we want all possible atlases or collections of charts which cover the space. And so now you can imagine taking the same space and say taking this region, which in this atlas is not an overlap, but then having another atlas where that region is an overlap, and then you have to demonstrate this smoothness for this region. So by considering all possible atlases, you actually have this smoothness criterion in terms of the transition functions affecting all parts of the underlying space. Okay, so that's one more reason why that weird abstract notion of maximal in terms of atlas is important. And then the other thing is I mentioned, I think briefly at the end, oh, this eraser sucks, and it's the only one in the room. Oh no, there's another one. Let's do it, ready? Oh, you're gonna draw two? Okay, you do it. All right, drop one to catch the other. These are probably terrible too. No, it's the board, Okay, anyway, the last thing I mentioned, which I'll just remind you because it's going to come into play today, is if we are lucky enough to be able to cover our space with a single chart, that's not always possible, but sometimes it is. So if we can get away with just using a single chart, then we can imagine a chart for our space and then another chart directly overlapping it, and then we can talk about taking the coordinates from one chart and creating a map to the coordinates for the other chart, and that is of course what we mean when we just talk about a coordinate transformation in a space. Okay. You probably haven't worked with too many spaces where you require more than one chart, so you're just used to saying I've got a set of coordinates, I transform them to a new set of coordinates, But what we're learning now is for some spaces, you actually have to do that in patches, okay? We won't work in too many contexts like that in this class, but it's important for you to be aware of those conditions, especially if you're ever doing something topologically non-trivial. Okay, so here we go. Every time I give this lecture, I get nervous because it's like, yeah, okay, for that reason. Jeez, I thought I just said what I had to say. Oh, no, I'm fine. Yeah, okay, yeah, good. Right, yeah, good. Yeah, I'm going to say it this way. Okay, so I'm going to start out by deriving a little result, which at the end you're probably going to be like, it's totally obvious. And that's fine, but we're going to sort of do it technically. And then I'm going to take that result and I'm going to put it aside for a moment and go to super deep mathematical abstract land. And at the end of our foray into super deep abstract mathematical land, we'll come back and pick up that little result and apply it to what we did in Mathland. And then we're going to go have fun with stuff that we're very comfortable with. Okay, so that's sort of the roadmap for today. So I'll tell you when to really fasten your seatbelts. For now, this is just going to be sort of stuff you've seen in calculus before. So let's talk for a moment about formally describing coordinate changes. So you can imagine that if we're transforming from some old coordinates x mu to some new set of coordinates x mu prime, then one way of conveying what that coordinate transformation is to give you the new coordinates as functions of the old coordinates. Okay? Now, previously, we would do something like this, where we would actually do this with some linear transformation that could be represented by a matrix. These were the lambda matrices. But for the most general coordinate transformation, what you're really trying to do is just give me the new coordinates expressions as functions of the old coordinates. And this is doing the exact same thing. Okay? But we're going to work with this more general context. Okay? So now what I want you to consider is a familiar result from calculus, and that is the chain rule, which was, of course, invented by George P. Chain, who taught at Ohio State University in the 40s. And what's hilarious about that is my partial differential equations teacher at Georgia Tech, Professor Herod, said that in class one day, and I believed him. And I later said that to fellow students who mocked me mercilessly. That's my failure Thursday story. Okay, so let's talk about the chain rule for a second. And so from good old one-dimensional calculus, you all know these are functions of single variables. So we've got g as a function of x, and then I'm going to have f as a function of g. And then what I want to know is how does f change with x? Of course, to figure out how f changes with x, I can talk about how g changes with x, and then how f changes with g. So formally, we would write that as df dg. dg dx. And you know, it's got that kind of feels right calculus sense in which, if I just cancel off the dg's, that's df dx. It's got to be the right answer. You know, but it actually is, okay? It's actually true. Now, one way that we sometimes notate this is that this is f compose g. And the idea here is that we can think of f and g as maps. We feed them something and they give us something back. And so the idea when you write it this way is that if I feed this something, say the value x, I first map it with g, and then whatever I get, I then map it with f. Okay? So let's write that down. This sort of nested function we'll write as f compose g, and we'll come back and use that on a couple of examples later on. Okay, and then this, of course, would just be the derivative with respect to x of f compose g. Now, this is the story as per Calc 1 and probably Calc 2, and then at some point in your calculus classes you realized the world was actually more than one-dimensional. There's not just x, but there's x and there's y and there's z and there's w and all those other wonderful coordinates. So we really need to see how this story plays out for functions of more than one variable. And so now consider several functions, f1, which are themselves functions of several functions. And I'll just do this for 2 as sort of a minimal case. Where here I have in mind that g1 is a function of 2 coordinates and g2 is a function of 2 coordinates. Okay. And then how does this nice little chain rule story play out if we're now working with not 1 but 2 independent variables, and then we're working with 2 intermediate functions, g1 and g2. And so we can ask, how does f1 vary with respect to x? And then alternatively, how does f1 vary with respect to y? And then of course, how does f2 vary with respect to x? And how does f2 vary with respect to y? So we have 4 questions we can ask. How do each of the components of f vary with each of the independent variables x and y? Okay? And then you can probably guess the answer. We find out how f1 varies with respect to g1, and then how g1 varies with respect to x, and we add to that how f1 varies with respect to g2, and multiply that by how g2 varies with respect to x. Okay? And then dot, 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 dot. Okay, anything mysterious in what I wrote? Anyone? Is it not obvious to anyone how you would fill in the rest of these dot, dot, dots? Good? Okay. This can all be encapsulated in some rather compact notation. We can write this as d of f nu. Actually, I'll write it this way. D by dx mu of f nu of g lambda, okay, where secretly this is g lambda as a function of x mu. Holy cow, look at that, indices everywhere. Secretly, of course, what I have in mind in these labels is that I'm always going to have as many functions g as I have coordinates x and y as I have functions f. So I can kind of label everything by a label which takes the same values, 1, 2, 3, 4. And of course, I'm using our Greek symbols because these are obviously going to eventually be connected to t, x, y, and z. Okay? And so this is a compact expression for the left-hand side. The right-hand side we can then express simply as partial f nu partial g lambda, partial g lambda partial x mu. Okay? Now let's just make sure this makes sense. So looking at the right-hand side, lambda is summed over. So whatever g I have here, I should have here, the same g here, and then I should add those terms together. That's exactly what I'm doing, g1, g1, and then g2, g2. The nu and the mu, I just pick values, and those are the same in all terms. So notice 1 and x, 1 and x. X would be x, y is x1, x2. Okay? So is everybody comfortable with the idea that that is a compact expression for what we would fill in right here in this story? Thanks for hiding your boredom. I appreciate it. Sit on the front row and yawn like a lion. Okay, all right. Now what we're going to do is we're going to think of G as a coordinate transformation. That is, instead of thinking of this G, which is indexed by something like lambda x mu, I instead am going to call this x mu prime as a function of x mu. Okay? That's just a relabeling. I mean, G is some function of the original coordinates, but G has as many components as the original coordinates. Okay, lambda takes as many values as this does. So I can take this story, and anywhere I'm using G, I can just instead think of it as I'm taking some old coordinates and I'm replacing them with some new coordinates. And then there would be some expressions that would tell me exactly how that coordinate transformation occurs. The only difference is I call this mu prime because that's the label we give to new coordinates. Primed is the new coordinates, okay? So in this story, what we can now say is that d by dx mu of f nu of x mu prime, so all I've done is replace that g lambda there with x mu prime, that's going to be equal to df nu dx mu prime dx mu prime dx mu. Okay? Now if you squint your eyes for a moment and say to yourself, what was that f? Well, what was that f thing that you started with? Was it really all that important? It's really not all that important. We're going to find that today f's are not that important. If you squint your eyes and you look at this carefully, what you'll notice is that d by dx mu is going to this. Where all I've done is I've sort of removed the f nu, the thing that everything is acting on. But another, perhaps more convenient way to write it, because we don't want to get confused and think that this derivative is somehow acting on that, because it's not. This derivative was acting on this f. I'm just going to do a very slight rewrite, and I'm going to say this. Okay? Where what we've just discovered is a very useful result, and that is, because people like these big acronyms for texting purposes, we just determined the TLFPD. Adria, what does the TLFPD stand for? You're savvy with the tech. Come on, girl. You can do it.
Transformation laws for partial derivatives.
Boom! Would you look at the notes in advance? That's awesome, yeah. So what we just discovered is how a partial derivative transforms when we go to a new set of coordinates, okay? So in this case, I'm actually transforming from the prime to the unprimed. If I say I start with a partial derivative in the primed coordinates, what would the partial derivative in the unprimed coordinates look like? Well, I take this and I act with this thing right here. Okay? You can obviously turn that around and instead write this, because the primed and the unprimed roles are completely interchangeable. Okay, so you could say if I start with the unprimed partial derivative and I do a coordinate transformation and I want to know what does the partial derivative look like in the new coordinates, I can take the old one and act with that, and it will give me the partial derivative in the new one. Okay? Is that kid a yo-yo? Oh, okay. All right, so not so bad, huh? You might have even guessed it. I mean, hell, you know, it's got that calculus sort of, I'm kind of dividing this, cancels, and I'm just left with that, and that kind of feels right. Okay? All right, so there's a nugget. Oh, man. And now it's going to get ugly. So fasten your seatbelts.
You're just trying to intimidate us.
I'm not trying to intimidate you. I'm trying to say that the next 20 to 30 minutes, you might feel like you're lost in a sea of arrows and maps. And I just want you to realize you will emerge from it feeling okay at the end, but don't get distraught if it hurts a little bit. Okay. All right, here we go. If you thought the picture I showed you last time was complicated in the last lecture, this one is going to really make that one look easy. So we have just discovered how something transforms under a general coordinate transformation. Okay? Happens to be the partial derivative. But what we would really like to do is figure out how vectors transform. Because remember, a very big part of our development of special relativity, which I promised you would play out again in curve space and general relativity, is establishing the transformation rules for quantities like vectors and dual vectors and tensors and so forth. So that's what we're starting to do now, is formally unravel how does all this play out in the case of general relativity and curve space. So the one thing that we know is that vectors, and it's incredibly important to remember this in the case of curved spaces, Kyle is going to remind us, where do vectors actually live?
They live in tangent space.
Yeah, they live in tangent space. We can't think of vectors as these arrows stretched out in space-time, because space-time might be all curved, and those things that are stretched out aren't really vectors that they don't satisfy the axioms of a vector space in the sense that we normally think of it. So we really, if we're going to talk about vectors, we've got to talk a little bit about tangent space. And so what we're going to do now is we are going to construct tangent space. Okay? Don't act too excited about that. Tangent space. Any questions? No, I'm just kidding. I wish it was that easy. It's not. Here we go. All right. So the one thing that's really weird about this approach is that you have to understand, remember, the notion of a vector exists independent of coordinates, right? We get in the car, we're really hungry, we drive to
IHOP.
IHOP. Okay, I don't even know what direction the closest IHOP is. It's that way. I was actually pointing in the correct direction the entire time. We want to drive, so we get in our car, we drive with a velocity vector, and we can all look at it, and we can all go, yeah, it's there, and it points that direction without ever referencing an XYZ. Okay? Of course, we are free to write down an XYZ and then go, oh, our velocity vector now has these components with respect to that XYZ coordinate system. Okay? So what I want to do is I want to try and get at a way to talk about vectors in tangent space without using coordinates. It's going to be a little abstract. And then we'll turn around and go, okay, but we use coordinates to do physics, so how do coordinates fit into the story? And then it'll get even more abstract. So here we go. So we're going to start with, we got to start with something. We're going to start with a manifold M, a point on the manifold P, because remember, tangent space is defined one point at a time, because one of the important things about curved spaces is that the tangent spaces don't have to be the same from one point to another. So we are defining tangent space at a single point, and then we're going to consider a curve, gamma, through the point P. This is going to be a curve that's in the manifold, so literally just you draw a one-dimensional line, curvy if you like, that's going to pass through the point P, okay? So let's get our picture started here. If I do this right, I'll get a lot of mileage out of it. If I do it wrong, I'll have to erase a bunch of stuff and draw it again. So there's our manifold M. There's the point P. This is really not that bad. Here's a curve gamma passing through the point P. I know you're wondering, why were you saying this is going to be hard? Okay, here we go. So first of all, when I talk about a curve, what I have in mind is that this is some parametrized curve through the space. That is, there's some quantity that we can tick up, and as we tick that quantity up, it moves us along the curve. Okay? So secretly what we have in mind is that there is some real line, and I will call that real line, I'll label that real line by lambda. Okay. And what we have is that the curve gamma is a map from values of lambda into points in the manifold M. Okay? So let me illustrate what that means. It means if you give me a value of lambda, say the value lambda p, this is a quantity in the real line. It's a value of lambda. But then the curve gamma takes this and it maps it, that's what the arrow means, to a particular point in the manifold M. So this thing right here is actually the map gamma. Okay? And technically it's how gamma acts on the point lambda p. Now what's important is that this map gamma is not going to give us just any points in the manifold, it's only going to give us the points along this particular curve. So this map is associated to this curve. Okay? What's better than one map? Two maps, exactly. So let us create another map. Why not? Why not? So let us now take the point P and let us map it to a point on yet another copy of R1, which I'm going to parameterize by alpha. Okay? And we're going to call this map F. And so now what we do is we feed into F a point P in the manifold. Okay? And then that's going to return for us a quantity on the real line. In this case, the value alpha P. Okay? Now, this F is just going to be completely arbitrary. It's just, you know, whatever function you like to write down that takes points in a space and returns points in R1, or returns values in R1. C infinity, just make it a really nice and smooth map. Important point about F, you can feed F any point in the manifold. Okay? There's no restriction on what points you can get put into F. When you use gamma though, gamma only gives you back points along the curve in question. Go ahead.
Does that mean F can't be the inverse of gamma?
Yes. Yes. Now, you might say to yourself, why two maps? Like, what is the value of having two maps?
What is the value of having two maps?
I'm glad you asked. I'm so glad you asked. Let us see if Chasen. You might recall from the last lecture, which was much simpler and abundantly clear, that we did something similar. We had a map into the manifold and then a map from the manifold into another thing. And so we had this little path we took. It's, oh, I don't like it here, let's go into the manifold. I don't like it in the manifold, let's go over here. And then we took that and we said, actually, we could just do this. And what is that? Just do this thing. See him going back carefully through his notes.
You sound like a South Park character.
South Park characters? Oh man, what South Park character would do GR? It's gotta be Cartman, it's gotta be Cartman.
Why?
Because he's the most curved.
It's just like
Hey guys, let's do this. What am I gonna do? All right. You got it, Jason?
We found
find some sort of like relation between those treatments?
Huh? Say it again? Sorry, I wasn't listening. I was telling you about the answer.
Oh.
Anybody want to tell him?
We could make a map from the lambda space to the alpha space.
Yeah, we could actually forgo the manifold entirely and consider just going straight from lambda p to alpha p, okay? The map that would do that for us technically is F compose gamma, okay? So let's go over this again. F compose gamma means I do the gamma map first, which means I take a value lambda p that's in R1, I gamma it, and then I F it, and the result is a value in R1. So after you've gammaed and F'd the value, you're really, this whole thing is just a function from R1 to R1. From like literally X to Y. Okay? Forgetting about the fact that there's this complicated mathematical thing in between called the manifold, okay? Okay, if you feel more comfortable putting in arguments and actual values, you feed F compose gamma lambda p and you get back alpha p, okay? Now, in words, and I want to be a little bit careful because I think when I start doing this, you see striking similarities to things we talked about last time, so I want to be very careful. This little thing right here, and the map to here, and then subsequently the map to here, these things are not charts. Okay? Remember, when we have a chart, we actually take a region which has the same dimensionality as the space, and we map it into a copy of Rn where the dimensionality of this is the same as the dimensionality of the manifold. Okay, here this is literally R1 and R1 no matter what the dimension of this is. So these are not charts, okay? The fact that these are one-dimensional is more akin to the fact that I'm thinking about a curve, a one-dimensional curve through the space, rather than trying to create these charts. Okay, so now we can ask the following question, which should be a meaningful question, and that is, what is DFT lambda? Okay. So let's think about that. If I change the value of lambda, I change the point P, but if I change the point P, I change the return value alpha. And so we can ask, what is the rate of change of this with respect to a change in this? And that's what I mean by DFT lambda. Okay? Where secretly we can also notate this to remind ourselves that this is actually the composition of two maps as the derivative with respect to lambda of F compose gamma. Where I have in mind here, and this is a point which will become clear in just a second, this lambda here is associated to this particular curve gamma. So if I write DFT lambda, I have in mind that I'm looking at this particular curve which is parameterized by lambda. That's why on the left you don't see reference to gamma, but it's secretly there. It's hidden in the fact that I'm referring to lambda. Okay. This is called the directional derivative of F along, and I'll call the curve lambda, yeah. Okay. So what you have in mind with a directional derivative, I can define a function over this manifold And then I could say, you know, what's the derivative of that curve? Or sorry, what's the derivative of that function? So say this is like this is a four-dimensional manifold. And then I can give you some function defined over the manifold. Well, normally you would say to me, well, I need coordinates because I need to be able to write this as t, x, y, z. But everything we're doing doesn't have coordinates. We're not talking about coordinates. So I can't do that. I can't write it, this is a function of coordinates and then take derivatives with respect to coordinates. So what we can do is we can say, I'm going to have a curve through the space and I want to know how does f vary as I move along that curve. If I pick a different curve, f might vary differently along a different curve. So this is what we mean by this idea of a directional derivative. Okay. Now, what we're going to do is we're going to consider not just a single curve through the point P, but now we are going to consider every curve that goes through the point P. And we'll just give them various labels. All right, so just fill this up with all possible curves passing through the point P. And what I would argue to you is that the set of directional derivatives, I'm going to call this lambda, d alpha, df beta, the set of all directional derivatives corresponding to the variation of some arbitrary function f along any of these curves at the point P. We're looking at the values of these derivatives at the point P. This set of directional derivatives forms a vector space. Okay. So let's see what we mean when we say that something forms a vector space. So there are some axioms associated with a vector space. And I'm not going to prove that this thing satisfies these, but many of them will be manifestly clear. If we take any two of these derivatives and we add them together, we should be able to express that as a third derivative. Okay. That is, we have the property of vector addition. If I add two vectors together, I should get another vector. I should be able to multiply one of these by a scalar and get yet another vector. So I have the action of scalar multiplication of one of these. I have associativity of the addition of two vectors. I have commutativity of addition. That is, v plus w and w plus v give me the same thing. I have an identity in the addition of vectors. Okay, what's the identity in vector addition?
Zero.
It's the zero vector. Good. And then we also have an inverse in the action of vector addition. And then we have a whole nother set of these for scalar multiplication. So we have a set of rules that the scalar multiplication operation has to satisfy. Okay. Now I'm not interested in trying to piece together, just by virtue of what you've done with working with derivatives in the past. Okay. You're probably familiar with the fact that you can add two derivatives together, and in some sense the net result gives you a derivative, and you can multiply a derivative by a scalar, and that's still a meaningful derivative, and adding things together doesn't matter which way you do it. The point here is that what we've done is we've taken the directional derivative of an arbitrary function along all of the paths that go through the point P. And we have demonstrated that those directional derivatives form a vector space. All right? Now here's the kicker. If I say I've got a path and I'm going to take the derivative, the directional derivative of something with respect to that path, what orientation of that do you think that directional derivative is going to be in association with the path?
Tangent?
Tangent to the path. So what we've just constructed formally is the set of all things tangent to the point P in the manifold. And furthermore, we demonstrated that that set of things forms a vector space, which is exactly what we want tangent space to be. We want it to be a true vector space. It satisfies all the axioms of a vector space. But it has to somehow be defined in terms of tangents to a point in a manifold. Okay? Alex?
So it's only valid at the point P?
Tangent space is only defined one point at a time. If I pick a different point in the manifold, I have to go through the entire construction of the tangent space for that point. Because these could literally be, the tangent spaces, so the example I gave when I first introduced this idea is if you take the surface of a two-sphere, if I pick a point here, the tangent space is tangent to that point. But if I pick a point here, you have the tangent space tangent to that. Those are two different planes. Okay? Don't get me wrong, the subject of GR is not taking a space, dividing it up into a continuum of points, and constructing the tangent space to each one. That's us. This is just kind of getting our bearings in terms of the formalism. But here you have it. This is sort of what I promised tangent space would be. It's a true vector space, and it really is defined in terms of quantities tangent to points in the space. And notice I've done this all magically without ever referencing coordinates. Okay? However, coordinates are important. In fact, much of what we want to talk about is how do things change when we change coordinates. So we're going to have to throw coordinates into this story. And in order to throw coordinates into this story, we are most likely going to have to make use of, oh, this is horrible, he's asleep. Can you what? Yeah, those. Mike, I drew your card. It's like the worst thing. You're so awake in the picture, but you're so asleep back there. Okay, so here, I'm going to ask you the question, and good luck. Oh, man. All right, everything that we've talked about has been without coordinates, but I want to add coordinates to the story. If I want to add coordinates to this story, what do you think I'm going to have, what special part of the manifold story do you think I'm going to have to make use of? Where do manifolds actually enter into the story? Or sorry, where do coordinates enter into the story of manifolds?
When you're dealing with more than just a single vector, when you have to compare things together.
Compare things together.
Is it when you bring in charts?
Charts, exactly. We're going to have to bring charts into the story. Okay. I made it a point earlier to say we are not working with charts with these things. Okay, we're just parameterizing a line or a curve. But coordinates are actually associated with putting down charts. It's charts, or utilizing charts in the manifold, which we know we can do because that's part of the definition of a manifold is that it should admit an atlas of charts. So what we're going to do, and I hope I've preserved this well enough, is we're going to use a chart for a region that at least encompasses the point P. Okay, so I'm going to take a hunk of the manifold, and then, this is going to have some, like U1, and then there's other charts. But we know that coming with a chart is a map to a copy of Rn. And in Rn, we are free to define these good old coordinates that we like to work with. So maybe x, y, and then add in as many as you need. And so this particular point in the manifold, using the chart map, will go to a certain point here, okay? Where, for lack of a better name, we might as well call that point x mu. And then we are also free to talk about the inverse map back to the point P. So if the map here for the chart, I'll call it phi. So phi of P takes us from the manifold into Rn. So it grabs a point in the space M and returns a point in Rn, whereas phi inverse grabs a point in Rn and gives us a point in the manifold M. Okay? Yeah.
What differentiates a chart more than it just being an n-dimensional, like, so your first transformations are kind of like one-dimensional charts. Is there some other kind of like difference between those lines? Because
well, remember this map has to have an open image in Rn. There's that qualifier. And then certainly on the overlap of charts, we have these transition functions which have to satisfy a differentiability condition. None of that comes into play in these maps.
Okay.
Okay? And remember, the inverse here is not necessarily, we talked about this last time in terms of that this has to be an injective map. It doesn't have to be a bijection, but if you're only considering the image of the points from the phi map, then on that set, you can consider the inverse map. So this is a lot of the details that we talked about last time. I don't want to go wade back into those for now. This is just a story of arrows. So let's talk about the arrows, okay? So what we can do now is coming back to this idea, we can make this even gooder, all right? Because what we can say is now that F compose gamma is secretly F compose phi inverse compose phi compose gamma. Okay? And let's just go through this. So what ultimately are we doing? We're taking a point here. We're using the gamma map to get us here. And then what I just interjected was said, well, before we come over here, let's use phi to carry this up here. Use phi inverse to carry us back down here. And then use F to carry us over here. So this string of maps is literally this path. Here, here, back to here, back to here. And again, this is one of those things mathematicians do, and I'm doing it, and I'm not a mathematician, but it seems completely unmotivated, but it'll all make sense in just a minute. But regardless of how motivated it seems, does this expression make sense? I've just added on this sort of closed loop of a phi inverse map.
Why does gamma inverse come before gamma? Or I mean phi. Why does phi inverse come before?
Well, you act with the thing to the right first. So gamma is the first map you do, and this is the gamma map. And then you act with phi, and then you act with phi inverse, and then you act with F. Okay? Now notice this is still a map from R1 to R1. Because at the end of the day, this is the thing you feed it, and this is the thing you get back. Okay? So to kind of map out the sequence here, we start with lambda p. We start with this point. We act with the gamma map, and that gives us a point in the manifold here. Okay? We take that point and we feed it into the phi map, and that's going to give us a value we're going to call x mu. That's up in here. And then we act on that x mu with the phi inverse map, and that's going to bring us back to the point P. And then lastly, we act with the F map, and that gives us the point alpha P. So that's what this little beast is doing for us. here comes the magic. Here's the magic. You're missing the magic. See the Cliff's Notes. Okay, so here comes the magic. DFT Lambda, that is the directional derivative of this arbitrary function f along some curve, say lambda. Okay. Where again, lambda is to be associated with gamma. These are sort of interchangeable labels. This is nothing but d by d lambda of, and one way to view this, f is f compose phi inverse, compose phi, compose gamma. Okay? Now this phi compose gamma starts with something in R1 and gives us back something in Rn, okay? Right, because the whole story starts here, that's in R1. We do a gamma map on it to get to P, but then we do a phi map to get to Rn. So at the end of the day, this is taking us from R1 to Rn. So we can label it as phi compose gamma mu. Because at the end of the day, the thing that we get after applying this map is something in Rn. It should have as many components as Rn does. Okay. And now what I can do is I can write this as the partial derivative of f compose phi inverse with respect to phi compose gamma mu d phi compose gamma mu d lambda. And that's just using the chain rule. That's using the chain rule on f compose gamma. Or that should be phi inverse. F compose phi inverse viewed as a function of phi compose gamma. Okay? All right, now we're going to make some identifications and then we're going to see the payoff. Phi compose gamma mu, as we mentioned, takes us from R1 into Rn. So one way we could label that is to say x mu of lambda. Okay? What are we doing? We're picking a value of lambda and we're getting back a value x mu. So we might as well just call it x mu of lambda. And forget about all these fancy arrows and intermediate points in the manifold, et cetera, et cetera. Since f compose phi inverse is a map, now let's look at this. Phi inverse takes something from here, and then f takes us to there. So this is a map from Rn to R. Okay. Then we might as well call this f of x mu. And then what we find, if we just use those labels in this expression, is that this comes down to the following directional derivative expression. DFT lambda is partial f partial x mu dx mu d lambda. Okay? Now f is completely arbitrary. So another way to write this maybe a little more concisely is that d by d lambda is dx mu d lambda d by dx mu. Where remember, like you can act on any arbitrary function defined on the manifold with this. Yeah, go ahead.
In the bottom left there,
Yeah.
aren't those different Fs though?
The
Like,
F's here,
yeah.
why would they be different F's?
Because the one on the right is defined as the F on the left composed with phi inverse. It's like it's different. It's a different thing, right? It's a function that takes something from R into R, where the one on the left takes it from R to R, R1.
So the F defined here is secretly this,
Yeah,
right?
which goes R1 to R1. Yeah.
Which is taking us from, yes, R1 to R1. And the F on the right is, I think, are you, it's, okay, yeah. So, yes, in terms of the, in terms of the formal way that you think about how these things are strictly defined, these two things are different, but there's a certain sense in which if these two things were the same, this expression can never be written, right? Because this is somehow being varied with respect to a parameter in R1, and this is somehow being varied with respect to the point in Rn, okay? But to the degree that once I give you a chart, which means that phi and phi inverse are well defined, and I define the function f, and it's just one function defined on the manifold f, this is understood to be f compose gamma, and this is defined to be, well, actually, no, actually, yeah, shit. Okay, sorry, my apologies. So technically speaking, this quantity right here is talking about how the function f varies no matter what direction you move in the manifold. Because all possible directions you can move from the point P are the directions in this patch Rn, or in the copy of Rn that you're being mapped to. Okay? So in principle, this quantity is capturing the variation of f in all directions. This is only capturing the variation of f along the particular curve parameterized by lambda. So there's a sense in which, yes, you have to think of what these things are as being different, but that they are built from the same underlying function on the manifold f. Because I can say I'm going to have a function defined on this manifold everywhere, but then I'm going to only consider its values given a curve in the manifold. Those are the values of f that I'm thinking of here. This is, I'm thinking of the values of f at all points in the manifold. Okay? But, that being said, given that the function I started this whole story with is arbitrary, we can write this expression. And now I want you to take a moment and think about this. This is a vector. Remember, that's what we talked about over here. We took all curves passing through the point P, And we said that the collection of all directional derivatives along all those curves forms a vector space. So this is just one of them. This is a vector in tangent space. These are indices which are contracted over. So if I were to try and give this an interpretation, I would call this the components of the vector. And what would that make this? So a vector is expressed in terms of components combined with what?
Basis.
They're basis vectors. So what we discover at the end of this circuitous discussion is that d by dx mu forms a basis in tangent space. That is, the set of partial derivatives forms a nice basis in tangent space. We call that the coordinate adapted basis because they're obviously intimately tied to whatever coordinates you happen to be working with. Okay? I know. Here's the good part. This is where we go, oh, okay. What have we done? We have identified in this abstract construction of tangent space, which is where vectors have to live, we have identified a set of basis vectors. But we know how those transform. If we know how one part of the story transforms, then repeating what we did in special relativity, we can go through a series of steps figuring out how everything else transforms. So let's see how that plays out. And this we can actually do a bit quicker because we're just sort of repeating what we've done before, just in a slightly different notation. So we studied a particular vector that is the tangents to curves defined by these directional derivatives, but an arbitrary vector should be expressible in terms of components combined with the basis vectors. Of course, we know how d mu transforms. Where remember, we have the shorthand that d lower mu is d by dx mu. Colton. Is Colton here? Is Colton not here?
No.
Chance. Chance. For a vector itself, how should a vector change under a change of coordinates?
Shouldn't it be invariant?
It should be invariant. So the vector itself should be invariant. We know how these transform. That means we can figure out how these transform. You remember this story? Good. All right. So what we can say is that v mu d mu needs to be equal to v mu prime d mu prime. That's invariance of the vector. D mu prime I can just express in this way using the transformation rule for partial derivatives. And that tells me that v mu prime should just be dx mu prime dx mu v mu. Okay? Where what we have in mind here is that dx mu prime dx mu. And actually, to avoid this being nasty, I'm going to write it like this. I'm going to put a mu here. Otherwise, I would end up with 4 mu's in this expression, and that is always bad for business. Dx mu, dx mu prime, dx nu, dx, and did I do the same thing there? No, I left it like this. Where this guy is by definition the inverse of this guy. Okay. So if this is something I'll call matrix, this would be the matrix inverse. Go ahead.
Those are all x's, not lambdas, yes.
Yes. Yeah, sorry, yeah, they're x's. They're all x's. Listen. And notice, just to be clear, I don't want to make this mu prime, mu prime, mu, and mu, because then this is a number. Okay, so that's why I've got a nu and a mu, so that at the end of the day, this is something with 2 indices. But the real reason why I keep those labels separate is because when I do this transformation, I don't want to use the same index here and here, because otherwise, when I write down this expression, it's going to have 4 mu's in it, and that's sort of misleading, because it makes you think you sum over all 4 of them simultaneously, which you don't. Okay? So what we found is that we can add to our story we can now add to our story that if I have vector components and I change coordinates, these are going to transform according to the following rule. So we have a transformation law for basis vectors. We have a transformation law for vector components. It follows the same sort of result that we found in special relativity. That is, the vector components transform with the inverse transformation that the basis vectors transformed. And that's why the combination is invariant. Okay. However, as you might anticipate, it gets gooder, because we can define a dual vector using the same prescription we used in special relativity, and that is if I have a dual vector, which can be expanded in some set of basis dual vectors, then the thing that we want to insist on is that dual vectors eat vectors and give us back numbers. And so in our notation from special relativity, we would write an expression that looked like that, where this is a basis vector, and that's a basis dual vector, and they're literally eating each other, and as long as their coordinate index values are the same, you get 1. If they're different, you get 0. This thing we're secretly calling now d nu, d by dx nu. This thing, we're going to give the suggestive name dx mu. Okay. And now the story is going to go exactly like it did in special relativity. Okay? This is a number. This is invariant. I know how this transforms, therefore I can figure out how this transforms. But if I know how this transforms, which is an arbitrary basis for dual vectors, then since dual vectors are invariant, I can know how this transforms and figure out how this transforms. Okay? So at the end of the day, we find that dx mu goes to dx mu prime, which is given by partial x, mu prime mu, dx mu. And omega mu goes to omega mu prime, which is partial x, mu, mu prime, partial mu. And so adding to our list of transformation rules, we have the transformation law for basis dual vectors and the transformation law for dual vector components. Okay? Where do you think we go from there?
It's a tensor.
We've got everything we need to do an arbitrary tensor, okay? Because what is an arbitrary tensor other than an object that has a collection of vector and dual vector indices? Okay? So without really thinking too hard about it, I could hand you an arbitrary tensor with some collection of vector and dual vector indices. And you can write down what the tensor components look like. And we're going to do the same thing we did in special relativity. That is, we know that the basis vectors and basis dual vectors are always going to take care of each other. So we can do all of our expressions in terms of just the components. That's the way we did everything in special relativity. Otherwise, you get this really nasty tensor product of theta, 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 and dx, dx, dx. So in terms of the components, if I give you a tensor and I say, what are the components in a new coordinate system? All you do is for every vector index, you apply the vector transformation rule. And for every dual vector index, you apply the dual vector transformation rule. And it's funny, like after a while you realize, oh, it's super easy to write down. All you do is you start by saying, I have 4 indices, so you do 4 dx dx's. Don't even try to assign subscripts yet. And then the thing you're transforming is this. And now all you literally do is you go through this and say, I want beta to become beta prime. Okay, so the beta has to get summed over, and I have to get a lower beta prime. And then you keep going. Alpha has to get summed over, and I have to get an alpha prime. Nu gets summed over, so I need a nu down here. So I need a nu prime there, which gives me back the upper nu prime. And then similarly, the nu and the nu prime. And there you go. There's your transformation law for the components of a mixed tensor, but you can obviously do this for an arbitrary tensor under an arbitrary coordinate transformation. Thank you. So I want to leave you with a very, 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 very important observation, which is going to occupy much of the next couple of lectures. Actually, I'll leave that there. So the observation is, first of all, in special relativity, we had this transformation rule that looked like this. Whereas in general relativity, where we have arbitrary coordinate transformations, we have a transformation law which looks more like this. Okay? Those two expressions are actually completely compatible. Because if you take an arbitrary coordinate transformation, which just so happens to correspond to a boost or a rotation, and you write down what this thing looks like, it will look like these lambda matrices. However, there are more transformations you can do here than you can do with the lambda matrices. Remember, the lambda matrices only connect inertial frames in rectangular coordinates to inertial frames in rectangular coordinates. These dx, dx mu, dx mu's, they can take us from one coordinate system to an arbitrary coordinate system, say curvilinear coordinates. Okay? It's completely arbitrary what you can do with these. All right? Now, one of the important things to observe is that when we do these lambda transformations in special relativity, the matrices that we write down are built from constants. Like literally, you say stuff like, I'm going to rotate by 35 degrees in the xy plane, and then that matrix has got like sine and cosine of 35 in it. They're just numbers. Okay? These transformations can be functions of the coordinates themselves. There's no reason why they have to be a bunch of constants. You can actually have it different at different points.
So it's a matrix, does it relate to the Jacobian?
Sure. Okay. I mean, you're aware of this, like if you write down the transformation from xy to r theta, right? X is r sine theta, or x is r cosine theta, y is r sine theta. Like that transformation actually has coordinate dependence. It's not just a bunch of constants in some linear transformation. Okay. Now, for anyone who's studied an iota of particle physics, you should recognize this as something we would call a global transformation. That is, you do the same thing everywhere at once. This is a more general local transformation. That is, it can actually be a slightly different thing at each point in space because it depends, its form depends on the coordinates themselves. So what this matrix actually looks like might be different here than it is over here. That is going to present us with an incredibly huge problem that we have to address, and I'm going to leave you with that. And that is, if we consider the derivative of a tensor, in the simplest case, we'll just take the derivative of a dual vector. If I do a coordinate transformation of the derivative of a tensor, and this is true for any tensor, I'm just using a very simple example for you. Well, it's true for almost any tensor. Then I can do the transformation because I know how d mu transforms. Okay, so I can replace, I started to erase it here, let's put it back. Got this nice ghosting that's helping us out for once. So I'm going to put in the transformation of d mu. And then I know how tensor components transform. And so this is going to be dx t nu prime nu. Okay? And then here is the fundamental observation. So when I actually write down what this looks like, it's going to look like this. Does anybody notice a particular problem with that? Ideally, what kind of object would we like for the derivative of a tensor to be? A tensor. How do I identify if something is a tensor?
It transforms like
If it transforms like a tensor. Does this thing transform like a tensor? No, it would if this were the only part. If this were the only part, that is exactly how the tensor would transform. But it doesn't transform like that because you get this extra piece. Now notice something very important. In special relativity, where these dx things are actually just a bunch of constants, in special relativity, what is this derivative? It's zero, because this thing is just a constant matrix. But in general relativity, where we allow our transformations to actually depend on position, that is, we allow our transformations to be local transformations, it turns out that the derivative of a tensor is not a tensor. And that's no good, because physics is uninteresting if you can't do derivatives. And as I've hopefully impressed on you, not working with tensors is a bad idea. So what we're going to have to do, and this is exactly what you do in particle physics when you do gauge theory, is we are going to have to create a new derivative. Create a new derivative that'll be called big D mu. Actually, I think in this class we're probably going to call it del mu. I can't remember, I'll have to look at my notes. But it'll either be big D, it's big D in particle physics, it might be del in general relativity. But we're going to have a new derivative so that when we use that new derivative on a tensor, that derivative actually gives us back an honest-to-God tensor. Okay? But it is going to require, just like in particle physics, the introduction of a gauge field. In particle physics language, this is where you find the photon coming from, starting with just charged matter and insisting on a local gauge invariance. We're going to find a gauge field comes out, we're going to give that gauge field interactions, and at the end of that story, we'll have general relativity. Okay. We're going to take a couple of weeks to get there.
Hey, just a heads up. Sigma Pi Sigma is having a lecture for like high school level on quantum computing over in the library.
Zheshwan Gong is giving it over in Betcher, right?
Yeah.
Do you guys want to take this?
Yes, please. We were about to ask you.
Yeah.